James Webb stared at a patch of sky smaller than a grain of sand held at arm's length. In that tiny sliver of darkness, it found thousands of galaxies. Some of them are so far away their light has been traveling since before our sun existed, and several of them should be impossible. We'll go to the edge of everything we can see. We'll meet galaxies that break the rules, black holes that grew too fast, and a force pushing the universe apart that no one fully understands. If you enjoy the journey, like and subscribe, it keeps these going. Prepare yourselves. We begin? The image loaded on a screen inside NASA's control room, and the scientists stared in silence. It was July 2022. The James Webb Space Telescope had just sent back its first deep field image. A deep field means the telescope locked onto one tiny, almost empty-looking patch of sky and stared at it for hours. The patch was so small that if you held a grain of sand at arm's length, it would cover that whole region. And inside it, Webb found thousands of galaxies. That alone would have been enough to make headlines, but that was the easy part. The moment the image came through, researchers started zooming in. They started cataloging what they saw, and almost immediately, someone noticed something wrong. Galaxies that should not be there were sitting right in the middle of the frame. Big ones, bright ones, fully formed ones. Galaxies that, according to every model scientists had spent decades building, had no right to exist that early in cosmic history. To understand why that matters, you need to picture how the universe is supposed to work. After the Big Bang, everything started as hot gas. Gravity slowly pulled that gas into clumps. Those clumps became the first stars. Those stars died and fed new generations of stars. Over hundreds of millions of years, those stars gathered into small galaxies. Then small galaxies merged into bigger ones. It was supposed to be a slow build, a gradual stacking of matter over billions of years, like a city growing from a single dirt road. Webb found skyscrapers on that dirt road. Some of the galaxies in that first image were so massive, so fully structured, that they looked like they had already been around for billions of years. But the light arriving from them told a different story. That light left those galaxies when the universe was only a few 100 million years old. That is about 2% of its current age. These galaxies were enormous at a point when, by every known rule, they should have barely started forming. Scientists did not panic in the hallway. They went quiet. Then they went back to their computers and started checking the math. Maybe the readings were off. Maybe the instruments were still being calibrated. Maybe there was a simpler explanation hiding in the data. There was no simpler explanation. A physicist named Alison Kirkpatrick, who had spent her career building the very models Webb was now challenging, described the moment openly. She said she was having a crisis of faith. She had dedicated years to understanding how galaxies formed, and the first real images from Webb were telling her those years might need to be rewritten. That is not something scientists say lightly. Webb was designed to be the most powerful space telescope ever built. It sits nearly 1 million miles from Earth, parked at a gravitational sweet spot where the Sun, Earth, and Moon all pull on it equally, keeping it perfectly still. Its mirror spans almost 21 feet across, which is about the height of a 2-story building. It collects light in infrared, which means it sees wavelengths of light that human eyes cannot detect at all. And on its very first real look at the deep universe, it found something that broke the rulebook. The galaxies were real, the data was clean, and the models were wrong. Scientists spent the next several months arguing about how wrong. Some said the models needed small adjustments. Others said the adjustments needed were anything but small. The deeper Webb looked, the worse it got. And the next thing it revealed raised an even harder question. How exactly does Webb see so far back in time in the first place? Light travels fast, so fast that we use it as a measuring stick for the universe. When you look at a star, you are not seeing it as it is right now. You are seeing it as it was when the light left it. The sun is about 8 light minutes away, which means the sunlight hitting your face right now left the sun 8 minutes ago. The nearest star beyond our solar system is about 4 light-years away, so you see it as it was 4 years ago. Webb points at objects billions of light-years away. That means it sees light that has been traveling for billions of years. When Webb images a galaxy 13 billion light-years away, it sees that galaxy as it looked 13 billion years ago. The universe itself is about 13.8 billion years old. So Webb is seeing galaxies that existed when the universe was barely a few 100 million years old. Essentially, it is watching the universe as a baby. That is already extraordinary. But the way Webb does it makes it even more remarkable. As the universe expands, it stretches light. Imagine drawing a wavy line on a rubber band, then stretching the rubber band. The waves get longer, more spread out. Light works the same way. Light from the earliest galaxies has been stretched so much during its journey that it has shifted completely out of the visible spectrum. It started as ultraviolet or visible light, but by the time it reaches us, it has been stretched into infrared. Human eyes cannot see infrared. Normal optical telescopes cannot detect it well either. Webb was built specifically to catch it. Its primary mirror is coated in a thin layer of gold. Because gold reflects infrared light better than almost anything else, the entire telescope sits behind a sun shield the size of a tennis court, 5 layers of material that blocks heat from the sun, earth, and moon, keeping Webb's instruments colder than almost anywhere in our solar system. It has to be that cold, because infrared is essentially heat radiation, and any warmth from the telescope itself would drown out the faint signals coming from across the universe. Think of it like trying to hear someone whisper from across a football field while standing next to a jet engine. Webb had to silence its own jet engine before it could hear the whisper. The whispers it picked up were ancient, light carrying information about the very first galaxies, the first stars, the first moments when the universe went from a formless fog to something structured and real. And here is where the story gets strange. When Webb picked up that ancient light, and scientists processed what it showed, the galaxies on the other end of that light were doing something they should not have been doing yet. They were already enormous, already organized, already packed with stars in the hundreds of billions. The standard model of cosmology, which is the set of equations scientists use to describe how the universe grew, predicted something very different. It predicted a universe full of small, irregular, chaotic young galaxies at that age. Galaxies still figuring themselves out. Messy, lumpy, dim. Webb found galaxies that looked ancient at an age when they should have been newborns. Every time the telescope sends back a new image, the team processes it and searches for these early objects. And almost every batch brings another one that does not fit. Another galaxy too big. Another structure too clean. The tool designed to confirm our understanding of the universe is quietly pulling that understanding apart, one image at a time. And the galaxies causing the most trouble are the ones scientists are now calling the impossible ones. A team of astronomers published a paper in early 2023, and the title alone caused a stir across the entire field of cosmology. They had found 6 galaxies. 6 massive, well-formed galaxies sitting at the very edge of the observable universe, existing when the cosmos was only 500 to 700 million years old. And the combined mass of stars inside them was staggering. One of them held roughly 10 times the number of stars in the entire Milky Way. Our galaxy took billions of years to build up that many stars. These objects had done it in a fraction of the time. The lead researcher, Ivo Labe, described it simply. He said finding these galaxies was like running a census and discovering that the newborns weigh the same as the adults. Picture the universe as a city under construction. You send a drone to photograph the site after just 1 week of building. You expect concrete foundations, maybe some steel beams. Instead, the drone comes back with photos of fully finished skyscrapers, complete with windows, lobbies, and people inside. That is the level of shock these galaxies produced. For a galaxy to be that massive that early, it would have needed to form stars at an absolutely extreme rate. Scientists measure star formation in solar masses per year, which means how many stars the size of our sun a galaxy produces every 12 months. Normal, mature galaxies like the Milky Way produce about 1 or 2 per year. Some active galaxies push into the hundreds. The galaxies Webb found would have needed to produce stars at rates of thousands per year, sustained without interruption from the very first moments of the universe. There is no known physical mechanism that allows that. Stars form when gas clouds collapse under gravity. But that process has limits. When stars ignite, their radiation pushes the surrounding gas outward, slowing down further formation. It acts like a natural brake. The early universe had that same brake. So how did these galaxies step on the gas so hard, so fast, and produce so many stars before the brake could kick in? Scientists have a few ideas. Some say the very first generation of stars, known as population 3 stars, which have never been directly observed, may have been so massive and so hot that they seeded the universe with the building blocks needed for rapid galaxy growth. Others suggest dark matter, the invisible substance that makes up most of the matter in the universe, may have clumped differently in the early cosmos, pulling gas together faster than current models allow. Nobody has a clean answer. What makes this especially unsettling is the sheer number of these galaxies. If Webb found 1 or 2, scientists could call them outliers, statistical flukes, weird exceptions that don't demand a new theory. But Webb found dozens, and the count is still growing. Every new patch of sky Webb examines seems to offer another one. The models being challenged here are not small guesses. They are the result of decades of observation, thousands of research papers, and some of the most careful scientific work in human history. Watching them bend under Webb's data is genuinely uncomfortable for the people who built them. But the galaxies themselves are only part of the problem, because sitting at the center of several of them is something even harder to explain. Before Webb launched, cosmologists were confident, carefully, quietly, professionally confident. They had a model, a framework called the Lambda Cold Dark Matter Model, which is the standard scientific description of how the universe formed and grew. It had been tested against decades of telescope data. It matched observations from the cosmic microwave background, which is the faint glow of radiation left over from the Big Bang, spread across the entire sky like a fingerprint of the early universe. It matched the distribution of galaxies we see today. It predicted the large-scale structure of the cosmos with remarkable accuracy. The model said the early universe should be full of small, dim, irregular proto-galaxies, scattered clumps of gas and young stars, barely holding themselves together, messy, immature, still building up the heavy elements they would need to grow. The big, organized, spiral galaxies like the Milky Way should only appear billions of years later, after enough time had passed for gravity to do its slow, patient work. Scientists were so confident in this picture that when Webb launched in December 2021, the goal was partly to confirm it, to see those early small galaxies in detail for the first time, to fill in the last missing pieces of a story they believed they already understood. Webb did not confirm the story. It brought back a different one. The specific mathematical problem goes like this. The model sets a limit on how much mass a galaxy can accumulate by a given point in cosmic history. That limit is based on how fast matter can collapse under gravity, how fast stars can form from gas, and how much of the universe's total matter budget was available in the early cosmos. When scientists measured the galaxies Webb found and calculated their masses, multiple galaxies exceeded that limit, some by a small amount, some by a factor of 10 or more. Exceeding the mass limit means one of several things. Either the model is missing something big, or the measurements are wrong, or some physical process exists in the early universe that we have not yet discovered. Researchers checked the measurements obsessively. They cross-referenced Webb's infrared data with observations from other telescopes. They ran the numbers through different analysis methods. The galaxies stayed massive. The violation of the model stayed real. One way to picture the problem: imagine a recipe that says a cake takes 4 hours to bake. You pull it out of the oven after 30 minutes and it's perfect. That doesn't mean you got lucky. It means something is wrong with the recipe. Either the oven temperature is off, or the recipe itself has an error, or there's an ingredient in the cake that nobody put in the recipe because nobody knew it existed. Cosmologists are now seriously debating all three possibilities. Some argue the early universe had conditions we don't fully understand yet, a different kind of turbulence or density that allowed faster structure formation. Others are questioning whether the model's assumptions about dark matter are accurate. A smaller group is raising an even more provocative idea that the age of the universe itself might be wrong. That last possibility is the most destabilizing of all, and it connects to data Webb is still collecting. But before we get there is another discovery buried inside these impossible galaxies that nobody expected to find. A chemical one. The word terrified is not something scientists use casually. These are people trained to stay measured, to speak in probabilities, to treat uncertainty as normal. So when multiple cosmologists began using words like crisis and panic in interviews and published papers after Webb's first year of data, the scientific community paid attention. The impossible galaxies problem is not one observation. It is a pattern, a repeating signal across dozens of separate findings from different research teams using different analysis methods, all pointing toward the same conclusion. The early universe was growing up far faster than it should have been able to. Every field has a foundational assumption, a starting point that holds everything else together. In cosmology, one of those assumptions is that structure in the universe formed gradually, driven by gravity and dark matter, building up over billions of years in a predictable sequence. Webb is challenging that sequence directly. Here is why that matters beyond just cosmology. Science builds on itself. The model that describes how galaxies form connects to the model that describes how stars form, which connects to how heavy elements like carbon and oxygen were produced, which connects to how planets formed, which connects to how life became possible. Pull on one thread hard enough, and the whole fabric shifts. If galaxies formed faster than expected, then heavy elements were produced earlier. That means the raw ingredients for rocky planets were available earlier. That means the window for life to emerge in the universe is potentially much wider than we thought, or, depending on how the physics shakes out, potentially much narrower. Scientists do not have a consensus answer yet. What they have is a growing list of galaxies that break the model and a growing urgency to figure out why. Some researchers are now calling this the galaxy overcrowding problem. The early universe, in Webb's images, looks more populated than it should, like a concert venue where twice as many people showed up as the venue was built to hold. The venue should not be that full. Something brought them all in ahead of schedule. One of the more striking findings came from a team that specifically hunted for the most extreme early galaxies, the ones pushing hardest against the mass limits. They found one object that, if the measurements hold, would represent a galaxy with a stellar mass equivalent to roughly 100 billion times the mass of our Sunday. All of that mass existing when the universe was less than 700 million years old. For reference, our Sun is about 4.5 billion years old, and it formed in a galaxy that had already been growing for billions of years before that. That one galaxy contains a puzzle that scientists are still actively trying to solve. Its existence demands a star formation process so efficient, so relentless, that it borders on physically unreasonable. And yet there it is. The data is solid. The instruments are working correctly. Webb is performing better than its designers hoped. The problem is real, and it is growing with every new image. But here is the part that shifts the whole conversation. These galaxies are ancient. Their light has been traveling for over 13 billion years. And what we are seeing is not just a record of what existed. It is a record of what the universe was doing. And in that record, something very strange was happening at the very beginning. Something that gets stranger the closer Webb looks. The light hitting Webb's mirror right now left its source before the Earth existed. Sit with that for a moment. Earth formed about 4.5 billion years ago. The Sun formed a little earlier than that. Some of the galaxies Webb is studying sent out the light we are now receiving more than 13 billion years ago. The planet you are standing on did not exist yet. The sun had not ignited. The entire solar system was still gas and dust floating somewhere in a universe that looked nothing like it does today. When Webb captures that light, it is doing something no camera in history has done as well. It is looking directly into the past. This is not a metaphor. Light travels at a fixed speed of about 186,000 miles per second. That speed never changes. So the further away something is, the older the light arriving from it must be. The universe is so enormous that this effect becomes extreme. A galaxy 1 billion light-years away is showing you what it looked like 1 billion years ago. A galaxy 13 billion light-years away is showing you a version of itself from 13 billion years ago. The observable universe, meaning the portion we can actually detect, stretches about 46 billion light-years in every direction from Earth. Not because the universe is only that big, but because light from anything further away has not had enough time to reach us since the Big Bang. Everything beyond that edge is invisible to us, and always will be. Webb sits inside that sphere of visibility and looks toward its outer edge, where the oldest light lives. What makes this scientifically powerful is also what makes it philosophically strange. When Webb images the most distant galaxies, those galaxies no longer exist in the form we see them. 13 billion years have passed. Those galaxies have evolved, merged with others, changed beyond recognition, or in some cases, may have been torn apart entirely. We are looking at ghosts, real, physical ghosts made of ancient light, and those ghosts are telling us something uncomfortable about the universe's childhood. The light from the most distant galaxies Webb has found carries a specific chemical signature. Elements like oxygen and carbon, which are forged inside stars over long periods of time, are showing up in these early galaxies at concentrations that should take far longer to produce. You cannot forge heavy elements without stars. Stars have to live their full lives, explode as supernovas, and scatter those elements into space for new stars and planets to absorb. That cycle takes hundreds of millions of years, minimum. Some of these early galaxies show evidence of having already completed multiple cycles of that process. Multiple generations of stars, born, lived, died, and enriched the galaxy, all within the first few 100 million years of the universe's existence. The timeline is physically uncomfortable, and it connects directly to what Webb found when it aimed at the absolute dawn of cosmic time, the era when the first light in the universe switched on. And what Webb found there was far more chaotic, far more energetic, and far more crowded than anyone had prepared for. The universe began in darkness. After the Big Bang, the cosmos was filled with an incredibly hot, dense fog of particles. Light existed, but it could not travel anywhere because the fog was so thick it absorbed everything instantly. For about 380,000 years, the universe was completely opaque, blind, a solid wall of energy and matter so compressed that nothing could move through it. Then the fog lifted. As the universe expanded and cooled, electrons slowed down enough to be captured by protons, forming the first hydrogen atoms. Once that happened, light finally had room to travel. The universe became transparent for the first time. The glow from that moment, the flash of the fog clearing, is still visible today as the cosmic microwave background radiation. It spreads across the entire sky as a faint signal that sensitive instruments can detect. It is the oldest light in the universe, a snapshot of the cosmos 400,000 years after its birth. But that first light was uniform, smooth, spread evenly across space with only tiny variations in density. No stars, no galaxies, no structure at all, just hydrogen and helium, expanding in every direction, with barely any clumps. Scientists call the period that followed the cosmic dark ages. For somewhere between 100 million and 200 million years, the universe stayed dark. No stars had formed yet. No light was being produced anywhere, just cold gas, slowly gathering under gravity. building up density in the places where those tiny variations in the early fog were slightly thicker. Then the first stars ignited. This moment is called the cosmic dawn, and Webb was specifically designed to look back far enough to catch it happening. What Webb found during cosmic dawn was far more dramatic than the models predicted. The first stars were enormous. Scientists calculate they were likely hundreds of times more massive than our Sunday. These objects burned hot and fast and violent, pouring out ultraviolet radiation that tore electrons away from the surrounding hydrogen gas. This process, called reionization, slowly cleared the remaining neutral gas from the universe, like a sunrise burning off morning fog. But the pace of that reionization and the sheer energy output of the objects driving it did not match what models expected. Webb's early observations suggest the first galaxies were pumping out ionizing radiation at a rate far higher than previously calculated. The universe's lights came on faster and burned brighter than anyone predicted. Some of those first galaxies were already producing stars at rates that should have taken far longer to achieve. The engine of star formation was running at full speed almost from the moment it switched on. That raises an immediate question. How do you get an engine running at full speed with no warm-up time? The leading idea involves the nature of the first stars themselves, their extreme mass, their short lives, their explosive deaths. But there is another object hiding inside several of these first galaxies that may have accelerated everything. Something with gravity so strong it could drive star formation across an entire galaxy. Something that, by every calculation, should have taken far longer to form than the universe had allowed. Every star in the night sky was born inside a cloud of gas. The process goes like this. A cloud of hydrogen gas, sometimes thousands of light years across, begins to collapse under its own gravity. As it collapses, it breaks into smaller clumps. Each clump keeps collapsing, heating up as it compresses, until the core becomes so hot and so dense that hydrogen atoms begin fusing together. That fusion releases an enormous amount of energy. The star ignites. One star forming takes millions of years from cloud collapse to ignition. Our sun took about 50 million years to fully form from the gas cloud it was born in. Now imagine a galaxy forming thousands of stars every single year, year after year, for hundreds of millions of years without stopping. That is what Webb found in the early universe. The technical term is star formation rate. Scientists measure it in solar masses per year. Our Milky Way, a fully mature galaxy with hundreds of billions of stars, currently forms about 1 to 3 solar masses worth of new stars per year. That is considered normal for a galaxy of its size and age. The galaxies Webb discovered from the early universe were running star formation rates of hundreds, and in some cases thousands, of solar masses per year, sustained, relentless, like a factory floor running at maximum capacity with no breaks and no slowdowns. To picture this, imagine a city that took 200 years to fully build. Now imagine another city appearing fully populated and fully built in about 4 months. The raw material input required, the speed of construction, the energy needed, all of it would shatter every rule in the building code. That is exactly the problem. When stars form, they produce radiation that pushes gas outward. This is called stellar feedback, and it acts as a built-in governor on star formation. The more stars form, the more radiation they produce, the harder it becomes for surrounding gas to collapse into new stars. The system regulates itself. Formation slows. That is how it is supposed to work. In the early universe, Webb's data shows that self-regulation was either absent or overwhelmed. Something was feeding these galaxies with gas fast enough and efficiently enough that the feedback mechanism could not keep up. Stars kept forming at extreme rates despite all the physics that should have slowed them down. One possible explanation involves the structure of dark matter in the early universe. Dark matter, which makes up about 85% of all matter, but cannot be seen directly, is thought to form large structures called halos. Gas falls into these dark matter halos and becomes the fuel for galaxy formation. Some researchers now suggest the first dark matter halos were denser and more concentrated than modern models assume, funneling gas into young galaxies faster than the standard picture allows. Another possibility is that the first stars, which were far more massive than stars today, superheated and compressed surrounding gas in a way that actually triggered more star formation rather than suppressing it. Their explosions as supernovae may have acted as pressure waves, squeezing nearby gas clouds and triggering new collapses. Both explanations have supporters. Neither is confirmed. The data from Webb is still being analyzed, new galaxies are still being found, and every new discovery adds another variable to an equation that was already hard to solve. But the star formation mystery becomes almost secondary when you look at what was already growing at the center of these early galaxies, something far harder to explain. In the center of almost every large galaxy in the universe, there is a supermassive black hole. The one at the center of the Milky Way is called Sagittarius A star, and it contains a mass equal to about 4 million suns. That sounds enormous, but compared to what Webb has been finding in the early universe, Sagittarius A star is modest. Some of the black holes Webb detected in early galaxies contain masses equivalent to hundreds of millions or even billions of suns, and they existed less than 1 billion years after the Big Bang. This is where the story becomes genuinely difficult to explain with known physics. Black holes grow by eating. They pull in gas, dust, stars, and anything else that comes close enough. As material falls toward a black hole, it heats up and forms a swirling disk of superheated gas called an accretion disk. That disk glows so brightly it can outshine the entire galaxy surrounding it. These active, feeding black holes are called quasars, and they are among the brightest objects in the universe. Webb has spotted quasars from so early in cosmic history that their host galaxies were barely formed. The black holes at the center of those galaxies were already enormous, already monstrous, already eating at full capacity. To grow a black hole to 1 billion solar masses, even feeding as fast as physics allows, takes an extremely long time. The maximum rate at which a black hole can eat is limited by the radiation pressure from its own accretion disk. When a black hole feeds too fast, the energy released blows the surrounding gas away, cutting off its food supply. Scientists call this the Eddington limit, and it acts as a natural speed cap on black hole growth. Running the math at the Eddington limit, starting from a small seed black hole, getting to 1 billion solar masses takes roughly 1 billion years of near constant feeding at maximum rate. Some of the black holes Webb found existed when the universe was only 400 to 600 million years old. The math does not close. Either the seed black holes were already enormous when they formed, which raises its own impossible questions, or they found a way to grow faster than the Eddington limit allows, which requires physics we have not yet discovered, or they formed through a mechanism that bypasses the normal process entirely. One proposed solution involves something called direct collapse black holes. The idea is that under certain early universe conditions, a massive gas cloud could collapse directly into a black hole without ever forming stars first. No stellar phase, no supernova, just a cloud of gas, becoming a black hole in one step. If this happened, it could produce seed black holes far more massive than the ones that form from dying stars, giving them a head start on growth. The evidence for direct collapse is indirect. Scientists have found some candidates, objects in the early universe, that show the right kind of radiation pattern, but nothing confirmed yet. What is confirmed is that the black holes are there. They are real, they are ancient, they are far too big for their age, and they are sitting inside galaxies that are themselves far too big for their age. Two impossible things, stacked on top of each other, and the growth timeline for both of them points to a problem that goes deeper than just the objects themselves. Let's make the timeline problem as concrete as possible. Imagine you are trying to build a skyscraper. The building has to be completed in 1 week. You have a crew, materials, and equipment. Under perfect conditions, with everything going right, you can maybe get the foundation done in a week. But you arrive on day 7, and find a finished skyscraper, complete with interior design and a rooftop garden. Your only conclusion is that either the skyscraper existed before you started building, or someone used a construction method you have never heard of. That is the black hole situation. The universe was about 400 million years old when one of the most distant and massive quasars Webb has studied existed. 400 million years sounds like a long time, but in cosmic terms, it is barely anything. The universe today is 13.8 billion years old. 400 million years is less than 3% of that total. For a black hole to grow to a mass of 1 billion solar masses in that time, starting from a stellar remnant black hole of perhaps 20 to 100 solar masses, it would need to grow at a rate that violates the physics of how accretion works. Every calculation arrives at the same conclusion. The available time is simply not enough. Scientists have explored workarounds. One is super Eddington accretion, the idea that in the extreme environment of the early universe, black holes may have been able to eat faster than the Eddington limit by having gas stream toward them along narrow channels, bypassing the radiation pressure that normally slows feeding. Computer simulations show this is physically possible under the right conditions, but sustaining it over hundreds of millions of years without the process shutting itself off is another challenge entirely. Another workaround is mergers. If black holes formed early and then merged with each other repeatedly, each merger would add mass quickly without the slow drip of accretion feeding. Two black holes of 1 billion solar masses each merging would instantly create a 2 to billion solar mass object. But for mergers to produce the objects Webb found by such an early time, the seeds themselves would have to be large, which loops back to the direct collapse problem from the previous chapter. Each solution requires its own set of assumptions, and each assumption pushes against something the models currently predict. Here is the part that makes researchers lose sleep. Webb is finding these oversized black holes in greater numbers than expected. The first few discoveries could be dismissed as rare exceptions, but the density of massive early quasars Webb is finding suggests they were actually common in the early universe, common enough that whatever process produced them was widespread and efficient. That does not sound like a fluke. That sounds like a rule nobody has written yet. And buried inside the era these black holes come from is a signal Webb detected that adds yet another layer to the mystery. A faint signature from the time when the universe itself was being transformed, when the first light was burning away the cosmic fog and rewriting the structure of everything. And inside that transformation, something strange was hiding. About 1 billion years after the Big Bang, the universe went through a transformation so total that it fundamentally changed the structure of all space. Before this transformation, the gas between galaxies was mostly neutral hydrogen. Neutral hydrogen is hydrogen where the electron is still attached to the proton. Neutral hydrogen is very good at absorbing ultraviolet light, so during this early period, the universe was foggy in a different way than the original opaque era. Light could travel, but ultraviolet photons kept getting absorbed by the neutral hydrogen gas floating everywhere between galaxies. Then the first stars and galaxies started pumping out enough ultraviolet radiation to strip those electrons away. Once an electron gets stripped from a hydrogen atom, that hydrogen becomes ionized. Ionized hydrogen does not absorb ultraviolet light the same way. So as the ultraviolet radiation spread outward from early galaxies, it cleared the neutral hydrogen gas, making the universe more and more transparent to high-energy light. Scientists call this the epoch of reionization. It reshaped the universe's atmosphere, so to speak, and made it the transparent cosmos we see today. By about 1 billion years after the Big Bang, the process was mostly complete. Webb was designed to peer into that era and watch reionization happen. What it found confirmed that galaxies were the primary drivers of the process. The ultraviolet radiation from early stars was stripping hydrogen and clearing the cosmic fog. But hidden inside that data was something unexpected. Webb detected that certain early galaxies were producing ionizing radiation at a rate far beyond what their visible star populations could explain. The stars inside those galaxies accounted for some of the ionizing output. Some of it, not all of it. There was an excess, a surplus of energy coming from somewhere inside those galaxies that the stars alone could not account for. The leading candidates for that excess energy source are the oversized black holes from the previous chapter. Active black holes, feeding at high rates, produce enormous amounts of high-energy radiation from their accretion disks. A galaxy with a monstrous young black hole at its center would pump out far more ionizing radiation than a galaxy of the same size without one. This connects everything we have discussed so far. The oversized galaxies, the extreme star formation rates, the two large black holes, and the unusual reionization pattern may all be symptoms of the same underlying process. A process in which the very first structures in the universe formed faster and more violently than current physics expects. But Webb's detection of the excess ionizing radiation also raised a separate question. If galaxies were reionizing the universe faster and more efficiently than the models predicted, the timeline of reionization needs to be adjusted. And adjusting the timeline of reionization has ripple effects across the entire history of the cosmos. Every piece of the standard model connects to every other piece. Change one, and you have to check everything downstream. Scientists are doing exactly that right now, running new simulations, adjusting parameters, testing the model against Webb's growing catalog of data. And the next chemical clue Webb found inside these galaxies forced another round of corrections. A clue written in elements that had no business being there. Oxygen should not have been there. Carbon should not have been there either. Neither should silicon, iron, or magnesium. But Webb found all of them, in significant quantities, inside galaxies that existed less than 1 billion years after the Big Bang. To understand why this is a problem, you need to understand where heavy elements come from. The Big Bang produced only the lightest elements, hydrogen, helium, and tiny traces of lithium. That is it. Everything else on the periodic table, every element heavier than those three, had to be forged inside stars. Stars are the universe's element factories. Inside a star's core, hydrogen fuses into helium. In larger stars, helium fuses into carbon. Carbon fuses into oxygen. Oxygen into silicon. Silicon into iron. Each step requires a more massive, hotter star and a longer burning time. When a massive star exhausts its fuel, it collapses and then explodes as a supernova. That explosion scatters the heavy elements the star spent its lifetime creating into the surrounding space. Those elements then become part of the next generation of gas clouds, which collapse into new stars and planets. Our sun was formed from gas that had already been enriched by previous stellar generations. The iron in your blood was forged inside a star that died billions of years ago. That entire cycle, from star birth to death to enrichment to new star formation, takes hundreds of millions of years minimum, even under favorable conditions. Webb found galaxies in the early universe with oxygen concentrations close to what we see in much older, more mature galaxies. For that oxygen to be there, multiple generations of stars had to have already been born, lived full lives, exploded, scattered their elements, and had their remnants incorporated into new generations. All of that in a galaxy that was less than 1 billion years old. Astronomers call the abundance of heavy elements in a galaxy its metallicity. High metallicity means a galaxy is chemically mature, enriched by many stellar generations. Low metallicity means it is young and chemically simple. The standard model predicts that the earliest galaxies should have extremely low metallicity, barely above the primordial hydrogen and helium baseline. Several galaxies Webb analyzed showed metallicity levels that belong to galaxies billions of years older. One interpretation is that the first stars were so massive and burned so fast that they ran through their entire life cycle in just a few million years, seeding the galaxy with heavy elements at extreme speed. Those first stars, the hypothetical population 3 stars that no telescope has directly observed yet, may have been hundreds of times more massive than our Sun and burned out in a cosmic eye blink, but produced enormous quantities of heavy elements in the process. If that is true, it would help explain the chemical signatures, but it adds more pressure to the timeline, because those population 3 stars would have had to form, live, die, explode, and enrich the galaxy, all before the galaxies we see in Webb's early images had formed the stars we do see. Event stacked on event, all racing to fit into a window of time that keeps feeling smaller. And all of these galaxies, these chemically complex, impossibly massive, star-forming machines, are not scattered randomly across the sky. They are arranged in a pattern, a vast, invisible structure that Webb is only beginning to map. The universe is not a soup. Stars and galaxies do not float randomly through space like raisins scattered in a bowl. They are arranged in a structure so enormous and so intricate that it makes the largest man-made structures look microscopic in comparison. Scientists call it the cosmic web, and it is the skeleton of the entire observable universe. Imagine stretching a giant spider web across a space 100 million light-years wide. The threads of that web are called filaments, and they are made mostly of dark matter, the invisible substance that makes up about 85% of all matter in the universe. Gas flows along these filaments, like water flowing down channels. That gas collects at the intersections, the nodes where filaments meet, and collapses into galaxy clusters. The flat, empty spaces between the filaments are called cosmic voids, and almost nothing lives there. The Milky Way sits inside one of these filaments. So do most of the galaxies we can see. The large-scale structure of the universe, when you zoom out far enough, looks less like a random cloud and more like foam in the ocean, intricate, connected, with vast empty regions separated by thin walls and threads of matter. Webb has been mapping the cosmic web in the early universe, and the results are reshaping what scientists thought they knew about how this structure formed. The standard model predicts that the cosmic web should have been much less defined in the early universe. The filaments should be thinner, the clusters smaller, the overall pattern less organized. Like comparing a rough sketch to a finished drawing, Webb found the finished drawing already in progress at a time when the sketch should still be underway. Several research teams have identified large filaments and protoclusters of galaxies in the early universe that are more massive and more organized than the models allow. Some of these structures contain dozens of galaxies already clustering together less than 1 billion years after the Big Bang. For that many galaxies to find each other and begin merging so early, the underlying dark matter scaffolding would have had to be in place even earlier, assembled with an efficiency the models do not predict. One image from Webb showed what appeared to be a massive protocluster, a dense region where a future galaxy cluster was already forming, at a time when the universe was only about 800 million years old. Surrounding it were filaments of galaxies stretching across hundreds of millions of light years, already laid out in the Webb pattern we associate with the mature universe. Dark matter is the key. Because dark matter feels gravity but does not interact with light or radiation, it can start clustering before ordinary matter does. It provides the invisible framework that ordinary matter then falls into. The question Webb's data raises is whether dark matter clustered faster in the early universe than the models predict, or whether dark matter behaves differently at early cosmic times than it does today. Either answer would require updating the models. And updating the dark matter model, even slightly, changes predictions across the entire field of cosmology. But as strange as the cosmic web findings are, something even more unsettling is buried in the numbers Webb is collecting about how fast the universe is growing right now, a measurement that refuses to agree with itself. No matter how many times scientists check it, the universe is getting bigger. Every galaxy is moving away from every other galaxy, carried along by the expansion of space itself. Picture a balloon with dots drawn on it. As you inflate the balloon, all the dots move apart from each other. No dot is at the center. Every dot sees every other dot moving away from it. The surface of the balloon is expanding, and the dots just go along for the ride. The universe works the same way, except in 3 dimensions instead of 2. Scientists have known the universe is expanding since the 1920s. What they have been arguing about ever since is exactly how fast. The expansion rate has a name, the Hubble constant, named after Edwin Hubble, the astronomer who first measured it. And for decades, measuring it accurately has been one of the central goals of cosmology. There are 2 main ways to measure the Hubble constant. The first way looks at the nearby universe. Astronomers measure the distance to certain types of stars and supernovae, whose brightness they know precisely, then compare that brightness to how bright they appear from Earth. From that, they calculate distance. Then they measure how fast those objects are moving away from us. Divide the speed by the distance, and you get the Hubble constant. This method gives a specific number. The second way looks at the ancient universe. Scientists study the cosmic microwave background, the leftover radiation from the Big Bang, and use it to calculate what the expansion rate should be today, based on the physics of the early cosmos. This method also gives a specific number. The problem is that the 2 numbers disagree. They do not disagree by a tiny rounding error. They disagree by enough that if both measurements are correct, one of them requires new physics to explain. Astronomers call this disagreement the Hubble tension, and it has been growing more serious for over a decade. Before Webb, some scientists hoped the tension would disappear with better measurements. Maybe the earlier telescope data had small errors that Webb's superior precision would fix. Webb made it worse. A team using Webb specifically checked the measurements that anchor the nearby universe method, the distance ladder that forms the foundation of that calculation. They used Webb's infrared vision to see through the dust and gas that can distort measurements, getting cleaner data than any previous telescope could provide. And their results confirmed the discrepancy. The 2 methods of measuring the universe's expansion rate still give different answers. The tension is real. This is significant beyond just being a measurement puzzle. A persistent disagreement like this, confirmed by multiple methods and multiple telescopes, almost always means something is missing from the model. Either the physics of the early universe was different from what we calculate, or the physics of the nearby universe is more complicated than we assumed, or there is a new ingredient in the cosmos that we have not yet identified. Some scientists are looking at dark energy as that missing ingredient, because dark energy, the mysterious force behind the universe's acceleration, may have more to offer than anyone originally suspected. And what Webb has found about dark energy is the piece of this story that reaches furthest into the future. The tension has a number. Scientists express the expansion rate of the universe in a unit called kilometers per second per megaparsec. 1 megaparsec is about 3.3 million light-years. The early universe method consistently gives a lower number. The nearby universe method consistently gives a higher one. The gap between them is about 8 to 10%. 8 to 10% sounds small. In everyday life, an 8% difference in a calculation barely matters. But in cosmology, where the laws of physics are supposed to be universal and precise, an 8% disagreement between 2 well-tested methods is enormous. It is the kind of gap that, in the history of science, has almost always signaled a discovery waiting to happen. When a similar kind of tension appeared in early 20th century physics, when different experiments about the nature of light and matter kept giving results that did not fit the existing models, the resolution was the discovery of quantum mechanics, a completely new framework that rewrote the understanding of reality at the smallest scales. The Hubble tension is not that dramatic yet, but the parallel makes physicists uncomfortable in a familiar way. Before Webb launched, the nearby universe measurements were based on the Hubble Space Telescope, an older instrument with impressive but limited infrared capability. There was a real possibility that some of the stars and galaxies used as distance markers were being slightly miscounted or slightly mismeasured because the Hubble Space Telescope could not fully separate individual stars in dense, crowded regions. Webb can. Its infrared resolution is sharp enough to pick out individual stars inside galaxies 30 million light-years away, regions that looked like blurred smudges to older telescopes. A team of astronomers spent over a year using Webb to recheck the fundamental rungs of the distance ladder, the specific types of stars used as distance markers, called Cepheid variable stars, and the Type 1a supernovae used for greater distances. They wanted to see if better measurements would shrink the tension. They published their results, and the tension stayed. Every rung they checked came back confirming the higher expansion rate. Webb's precision removed the possibility that the disagreement was a measurement artifact. The discrepancy was not caused by blurry data or uncorrected errors. The two methods give different answers because the universe is genuinely behaving in a way that one or both methods does not fully capture. That means either the early universe was different from what the cosmic microwave background calculations assume, or the way the universe has been expanding over the past several billion years has been influenced by something we have not fully accounted for. One candidate for that something is a change in dark energy. Dark energy makes up about 68% of everything in the universe. It is the name scientists give to whatever is causing the universe's expansion to accelerate. And the simplest assumption, the one built into most current models, is that dark energy is constant, same everywhere, same at all times. A fixed background pressure pushing space apart at a steady rate. Webb's data, combined with observations from other telescopes, is now challenging that assumption. And if dark energy is not constant, the consequences reach far beyond just the expansion rate. They reach into the future, far into the future, into the ultimate fate of everything. The universe is not just expanding, it is expanding faster over time. In the early universe, gravity was the dominant force. The mutual pull of all the matter in the cosmos was slowing the expansion down, working against the outward momentum left from the Big Bang. For the first several billion years, the universe expanded, but gravity was putting on the brakes. Then, about 5 billion years ago, something changed. The expansion stopped slowing down. It started speeding up. The cause of that acceleration is what scientists label dark energy. We do not know what dark energy actually is. We have never detected it directly. We only know it exists because the expansion is accelerating and something has to be pushing it. Dark energy is the label on the unknown ingredient. The acceleration has a consequence that plays out over astronomical timescales, far beyond anything humans will witness. But understanding it changes how you think about the universe's future. Right now, galaxies beyond a certain distance are already moving away from us faster than light can travel between us and them. That is possible because space itself is expanding, and there is no speed limit on the expansion of space, only on the movement of objects through space. Those distant galaxies are not racing away through space. Space between us and them is growing, carrying them along. As the acceleration continues, more and more galaxies will cross that threshold. Their light will never reach us again. Over tens of billions of years, the observable universe will shrink, not because the universe is getting smaller, but because the expansion is carrying things beyond our reach permanently. In about 150 billion years, the only galaxies visible from Earth, assuming Earth still exists and assuming anything on it could still observe, would be the galaxies in our immediate local group, the Milky Way and its closest neighbors. Everything else will have crossed the cosmic horizon. The billions of galaxies Webb sees today will be invisible, not because they are gone, but because the universe will have carried them beyond the boundary of what can ever be seen from here. Eventually, even the stars in our own galaxy will burn out. The last red dwarf stars will die in about 100 trillion years. After that, the universe will be cold, dark, and filled only with stellar remnants, white dwarfs, neutron stars, and black holes. slowly radiating away their last energy over inconceivably long timescales. This is called the heat death of the universe, and it is the destination that the current acceleration points toward. But all of that assumes dark energy stays constant, that its pressure remains steady and unchanging forever. Webb's latest data is raising the possibility that dark energy does not stay constant, and if it changes, the entire future of the universe changes with it. Some possibilities are stranger and more extreme than heat death. Some of them are far faster. Dark energy is the most abundant thing in the universe, and scientists cannot tell you what it is. It makes up about 68% of everything that exists. For comparison, all the ordinary matter in the universe, every star, planet, gas cloud, and dust particle, makes up only about 5%. Dark matter makes up another 27%. Dark energy is the dominant ingredient in the cosmos, and its fundamental nature is completely unknown. The simplest model of dark energy treats it as a property of empty space itself. The idea is that even a perfect vacuum, a region of space with absolutely nothing in it, carries a fixed amount of energy. Einstein's equations allow for this. Scientists call it the cosmological constant. The mathematical symbol for it looks like the Greek letter lambda. It represents a constant pressure pushing space outward, the same everywhere, at all times, forever. This model is elegant. It fits the data well enough to be included in the standard cosmological model, and for decades, most scientists assumed it was probably right, even without understanding what actually generates that vacuum energy. Webb, combined with a separate survey of the universe called the Dark Energy Spectroscopic Instrument Survey, released results in 2024 that introduced serious doubt. The data suggested that dark energy may have been stronger in the past and may be weakening over time. The expansion of the universe has not been perfectly steady. When scientists mapped how the expansion rate changed over billions of years, the curve did not match what a constant cosmological constant would produce. There were deviations, small ones, but statistically significant, enough that the constant explanation started looking insufficient. If dark energy is changing, it means the universe's fate is not what the simplest model predicts. A dark energy that weakens over time could eventually allow gravity to win, slowing and potentially reversing the expansion. A dark energy that strengthens over time leads somewhere far more dramatic, a scenario called the Big Rip, where the accelerating expansion eventually becomes so powerful that it tears apart galaxy clusters, then galaxies themselves, then solar systems, then planets, then individual atoms, ripping the fabric of space faster than any structure can hold itself together. The Big Rip is a real scientific hypothesis, and Webb's data has not ruled it out. What Webb has done is put the cosmological constant model under genuine pressure for the first time with data this precise. The deviation from a constant is not enormous, but it is consistent. Multiple analysis teams working on the same dataset have found the same signal. Scientists are being careful. One dataset is never enough to overturn a foundational model. More observations are needed, more analysis. Other telescopes will check the results. The next few years of Webb data will either strengthen the signal or dissolve it. But the possibility that dark energy is evolving, that the force driving the universe apart is itself changing as time passes, is now something scientists are actively investigating instead of casually dismissing. And the implications go well beyond the expansion rate, because a changing dark energy means the universe's past was also different from what the standard model calculates. The history of structure formation, the timing of galaxy growth, the development of the cosmic web, all of it depends on how dark energy behaved billions of years ago, which connects directly to what Webb is showing about the universe's largest known structures, objects so vast they challenge the very idea of a smooth, uniform cosmos. Scientists built the standard model of cosmology on a single quiet assumption: that dark energy is boring, constant, unchanging, the same in every corner of space, the same in every era of time. a fixed background hum underneath the entire universe, steady as a heartbeat, never fluctuating, never varying. The cosmological constant. That assumption made the math clean. It made predictions possible. It gave scientists a stable foundation to build everything else on top of. Webb is now pulling at that foundation. The signal is subtle but persistent. When researchers map the history of cosmic expansion using Webb's data alongside the Dark Energy Spectroscopic Instrument Survey, the universe's growth does not follow the perfectly smooth curve that a true cosmological constant would produce. The curve bends slightly differently across different eras. The deviation is small enough that earlier, less precise telescopes could not have detected it. Webb's precision is sharp enough that it shows up. To picture what a changing dark energy means, think of a river current. If the current is constant, you can predict exactly how fast a boat will travel from point A to point B. But if the current changes strength along the route, sometimes stronger, sometimes weaker, your prediction breaks down. The boat arrives at a different time than expected, and you have to go back and figure out what the current was doing at every point along the journey. Dark energy is the current. The universe's expansion history is the journey, and Webb is showing that the arrival time does not match the prediction. If dark energy was stronger in the past and is weakening now, then the universe expanded more aggressively in earlier eras than the cosmological constant model assumed. That extra push in the early universe would have compressed and energized structures differently, affecting how galaxies formed, how fast dark matter clustered, how quickly the cosmic web assembled itself. Every timestamp in cosmic history would shift slightly. Shift them enough, and the impossible galaxy's problem starts looking less impossible. If the universe had more energy driving its expansion in its youth, it may also have had conditions more favorable to rapid structure formation. The galaxies that seem too massive for their age might fit inside a revised timeline, where the universe's early expansion was more turbulent and energetic than we calculated. Some researchers think this is the key that ties everything together. One evolving dark energy model, if confirmed, could simultaneously explain the impossible galaxies, the reionization excess, the oversized black holes, and the Hubble tension. All four mysteries solved by a single revised understanding of the force that dominates the universe. That is an elegant outcome. Scientists love elegant outcomes. The problem is that confirming it requires far more data than Webb alone can provide. It requires matching Webb's galaxy observations with independent measurements of the expansion rate, the distribution of matter, and the large-scale structure of the cosmos. Several major surveys are underway or planned to do exactly this. Until those results come in, dark energy remains the universe's most powerful and least understood occupant. And the universe's largest known structures, things so enormous they should barely exist within a universe this smooth, are adding yet another layer to the mystery. The Milky Way is enormous. It spans about 100,000 light-years across and contains somewhere between 100 billion and 400 billion stars. It takes light 100,000 years to cross it from one edge to the other. By any human standard, it is incomprehensibly large. In the cosmic web, the Milky Way is a minor neighborhood. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain anywhere from dozens to thousands of individual galaxies, all held together by gravity and immense quantities of dark matter, wrapped in a diffuse cloud of superheated gas, millions of degrees hot. That gas cloud, called the intracluster medium, is so hot it glows in X-rays. The total mass of a large galaxy cluster, counting its galaxies, gas, and dark matter together, can reach 1,000 trillion times the mass of our Sunday. 1,000 trillion. Picture stacking 1,000 Milky Ways inside a single structure, then adding 100 times more dark matter and gas on top of that. Webb has been observing galaxy clusters in the early universe with a level of detail that previous telescopes could not match. And what it keeps finding is that large, organized clusters were already forming when the universe was less than 2 billion years old. That is early, very early. According to the standard model, Structures that massive should require far more time to assemble from the gradual merging of smaller groups. When two galaxy clusters collide, the event unfolds over hundreds of millions of years. The galaxies themselves mostly pass through each other, because the space between individual stars inside galaxies is so vast that direct collisions are extraordinarily rare. But the hot gas clouds of the two clusters slam into each other at millions of miles per hour. The collision creates a shockwave. It separates the gas from the dark matter because the gas interacts with itself and slows down, while the dark matter, which barely interacts with anything, passes straight through. The result is a separating smear of matter, galaxies and dark matter on one side, a glowing blob of shocked gas falling behind. The most famous example of this is the Bullet Cluster, a pair of clusters that collided about 150 million years ago and whose aftermath was captured by previous telescopes. It provided some of the best evidence that dark matter is real, because the mass distribution after the collision clearly showed matter separated from the visible gas. Webb has found multiple examples of colliding and merging clusters in the early universe, and their structure is already more complex than the models predict for that age. The clusters are more massive, more organized, and more numerous than they should be. Each discovery reinforces the same pattern emerging across every type of structure Webb examines. The universe built big things faster than the models allow. And then there are the places where it built almost nothing at all. Regions of space so empty they challenge the model from the opposite direction. Something enormous was not where it should have been, and its absence is just as alarming as everything else. Empty space is expected. The cosmic web has voids, the large regions between filaments where almost no galaxies live. Voids are a natural part of how structure forms. Matter flows toward the denser filaments and clusters, leaving the regions in between gradually emptier over time. The largest known void in the observable universe is called the Bootes void. It sits about 700 million light-years from Earth and spans roughly 330 million light-years across. To cross it, traveling at the speed of light would take 330 million years. Astronomers discovered it in 1981, and it has been puzzling researchers ever since, because even by the standards of cosmic voids, it is exceptionally large and exceptionally empty. A standard void of that size, formed by matter flowing outward towards surrounding filaments over billions of years, should still contain a scattering of galaxies inside it. Stragglers, background objects, random distributions of matter leave some behind even in emptying regions. The Bootes void has very few of those. It is far emptier than statistics predict. Webb has been studying the distribution of galaxies around structures like this, mapping how matter is arranged on the largest scales. And in the early universe, it is finding voids that are both larger and emptier than the models predict for their age. Voids form when matter flows away toward higher density regions. The speed of that flow depends on the strength of gravity in the surrounding areas and, critically, on the behavior of dark energy. A void that grew too large too fast suggests that matter evacuated it more quickly than expected, which could point to a different balance of forces in the early universe than the model assumes. The Bootes void is not the only example. Multiple large-scale surveys have identified similarly oversized empty regions, and some researchers have begun using the term supervoids to describe the most extreme cases. Webb's ability to count galaxies precisely at great distances is helping to map the true depth of these structures in a way that was impossible before. One particularly striking finding involves the alignment of these large voids with the large-scale flow of matter across hundreds of millions of light-years. The pattern of emptiness and density is not random. It has a direction to it, a preferred axis along which the largest structures seem to align. That alignment is something the standard model does not predict. A universe that grew from a smooth, uniform Big Bang, with only tiny random variations as its starting point, should produce large-scale structure that looks the same in all directions. No preferred axis, no special direction. Statistical bumps and patterns, yes, but no consistent orientation across vast distances. Webb's data is now feeding into a question that was already making cosmologists uncomfortable. A question about whether the universe looks the same from every angle at all, and the answer coming back is stranger than expected. The universe is supposed to be isotropic. Isotropic means the same in all directions. Spin around in a full circle, and the universe should look statistically identical no matter which way you face. Same density of galaxies, same expansion rate, same laws of physics operating the same way. The assumption of isotropy is baked into the foundations of modern cosmology. Without it, the math of the Big Bang and cosmic expansion becomes enormously more complicated. With it, the universe is symmetric and manageable. Several datasets, both before and after Webb launched, have been quietly suggesting that the universe might violate that symmetry. One signal comes from the alignment of galaxy spins. Galaxies rotate. Some rotate clockwise, some counterclockwise when viewed from a given perspective. In a truly isotropic universe, these spins should be random, with roughly equal numbers rotating each way in any given region of space. But surveys mapping galaxy spins across hundreds of millions of light years have found a slight statistical preference for one orientation over another in specific regions of sky. The preference is small, but it is consistent across multiple analyses. Another signal comes from the expansion rate itself. When scientists map the Hubble constant in different directions of the sky, the values should all be the same, because the universe should expand uniformly in every direction. Some analyses of distant quasars and galaxy surveys have found that the expansion rate appears slightly higher in some directions and slightly lower in others. A hemispherical asymmetry in the universe's growth. A third signal comes from the cosmic microwave background, the ancient radiation fingerprint of the Big Bang. The pattern of temperature variations in that radiation has some large-scale features, a specific alignment of the warmest and coldest regions that should not be aligned with anything in the nearby universe if the cosmos is truly isotropic. They are slightly aligned. This is called the axis of evil, which is not a political term but a cosmological one, coined by researchers who found the pattern troubling enough to give it a dramatic name. Webb is adding to this picture by providing the highest resolution mapping of galaxy distributions at the greatest distances ever achieved. The data is still being processed. Full results are not yet published. But early analyses suggest the galaxy distribution at extreme distances shows subtle, large-scale patterns consistent with the other isotropy violations found in lower resolution surveys. None of these signals is individually overwhelming, but the fact that multiple independent datasets, measured using different methods, different instruments, and different targets, all point toward a similar asymmetry, is a pattern scientists cannot responsibly ignore. If the universe does have a preferred direction, the implications collapse downward through the entire model. A non-isotropic universe would require a very different origin story. Something in the Big Bang itself, or in whatever preceded it, would have to have imposed that asymmetry. The equations change, the predictions change, the history of the universe changes, and some of the tools Webb is using to study this would not work without one of the strangest effects in physics: the ability to see objects that are actually behind other objects, using the universe's own geometry as a lens. Gravity bends light. Einstein predicted this in his theory of general relativity, published in 1915. The prediction was confirmed in 1919 when astronomers observed starlight bending around the sun during a solar eclipse. The sun's gravity warped the path of light from distant stars just enough to shift their apparent positions in the sky. The measurement matched Einstein's equation almost perfectly, and it made him famous overnight. That same effect operates at cosmic scales, and Webb is using it as a tool. When light from a very distant galaxy travels toward Earth and passes near a massive object, such as a galaxy cluster, the gravity of that massive object bends the light around itself. The distant galaxy's light curves around the cluster from multiple directions and converges near Earth, producing multiple images of the same galaxy arranged in arcs or rings around the cluster. The cluster acts as a natural lens, magnifying and distorting the image of whatever is behind it. Scientists call this gravitational lensing. When it produces visible arcs or rings, it is called strong gravitational lensing. When it produces only a subtle distortion of shapes across large areas, it is called weak gravitational lensing. Webb has turned gravitational lensing into one of its most powerful observational tools. Because Webb sees in infrared, and because it has the highest angular resolution of any space telescope ever built, it can detect lensed objects that were completely invisible to previous instruments. Objects so faint and so distant that without the magnifying effect of the foreground cluster, they would produce no detectable signal at all. Using galaxy clusters as lenses, Webb has imaged galaxies from the first few 100 million years of the universe's history, with a level of detail that would otherwise require a telescope physically impossible to build. The cluster does the magnifying work for free. In some observations, the same galaxy appears 3, 4, or 5 times around the lensing cluster, each image showing the galaxy from a slightly different angle, bent around the cluster by different paths. Scientists can use these multiple images to reconstruct the true shape and structure of the galaxy behind the lens, essentially building a three-dimensional picture from multiple bent views. One of the most striking images Webb produced using this technique showed a galaxy from less than 1 billion years after the Big Bang in enough detail to resolve individual star-forming regions inside it. Clumps of young stars, distinct regions of gas and dust, structural features that normally require studying nearby galaxies to see, all of it visible because a galaxy cluster several billion light-years closer acted as a cosmic magnifying glass. Beyond the individual science, lensing also maps the dark matter inside the lensing cluster itself. The strength and shape of the lensing effect depends on how mass is distributed inside the cluster, including the invisible dark matter. By modeling the lensing precisely, scientists can map where the dark matter sits inside the cluster with more accuracy than any direct measurement could achieve. Webb is producing the most detailed dark matter maps of galaxy clusters ever assembled. And those maps are revealing distributions of dark matter that in some clusters do not match what the standard model predicts. One more tool in the list of things quietly challenging the model. But the most singular discovery Webb made using lensing involved a single star, the most distant individual star ever detected. And its existence tells a story that reaches all the way back to the universe's first generation. Earendel. The name comes from an Old English word meaning morning star or rising light. A team of astronomers gave it that name after detecting it in 2022, and it fits, because Arundel is the furthest individual star ever detected, and its light has been traveling toward us since before the Earth existed. Arundel sits about 12.9 billion light-years from Earth. Its light left it when the universe was only about 900 million years old. Everything in the universe was younger. The Milky Way itself was still forming. The sun would not ignite for another 8 billion years. Detecting a single star at that distance should be impossible. Individual stars are too small and too faint to be seen across billions of light-years, even with Webb's power. The only reason Arundel was detectable is because a massive galaxy cluster sitting between us, and it aligned almost perfectly with the star's position, creating an extremely precise gravitational lens. The alignment was so exact that the lensing effect magnified Arundel's light by a factor of thousands, boosting it far above what any telescope could otherwise capture. Webb followed up on the original detection made by the Hubble Space Telescope and gathered far more detailed data. Webb's infrared capabilities allowed scientists to analyze the color and spectrum of Arundel's light, which reveals information about the star's temperature, size, and chemical composition. The results were significant. Arundel appears to be an extremely massive, extremely hot star, potentially a class of star called a blue supergiant, which burns at temperatures many times hotter than our Sun. Stars like this are rare even in the modern universe, They burn fast and die young, exploding as supernovae after just a few million years. Finding one from such an early era confirms that the early universe was producing stars at the extreme end of the mass spectrum. Even more intriguing, the analysis of Arundel's spectrum suggests it has a companion, a second star orbiting it, close enough that the two are likely gravitationally bound. Studying binary star systems from this early era could provide clues about how the first stellar populations formed and evolved. Arundel is also significant for what it is not. It does not appear to be a population 3 star, the hypothetical first generation of stars made purely of hydrogen and helium with no heavy elements. It shows signs of at least some chemical enrichment, meaning the gas it formed from had already been through at least one previous generation of stars. Even at 12.9 billion light-years away, in the very early universe, the gas had already been enriched. That is yet another sign that whatever happened in the universe's earliest moments, the first stellar generations came and went so quickly that even objects from this early era are already second or third generation. And the galaxy Arundel lives in has features that add to a discovery Webb keeps making in the early universe. Something that started appearing in image after image and shocked scientists every time. Early galaxies that look exactly like galaxies from today. The Milky Way took billions of years to look the way it does. At least, that is what the models predicted. Flat, disc-shaped, organized into spiral arms. A calm, rotating structure where stars orbit the center in orderly paths. The kind of peaceful, mature architecture that develops only after a galaxy survives billions of years of mergers, turbulence, and gradual settling. Webb keeps finding galaxies that look like the Milky Way from when the universe was a fraction of its current age. In late 2022 and throughout 2023, multiple research teams identified disc-shaped galaxies in Webb's images from the early universe. Some of them existed less than 2 billion years after the Big Bang. Their disks were thin, their stars were organized, their rotation curves, the pattern of how fast different parts of the galaxy orbit its center, matched the flat, orderly rotation of mature spiral galaxies in the nearby universe. This was deeply unexpected. The early universe is supposed to be chaotic. Galaxy formation at that age should be driven by constant mergers, violent gas inflows, and intense radiation from quasars and massive star-forming regions. All of these processes disrupt disk structure. They heat up the stellar orbits, thicken the disk, and destroy the thin, flat organization that characterizes galaxies like the Milky Way and Andromeda. For a galaxy to maintain a thin disk in those conditions, it needs to be somehow protected from the chaos around it. It needs gas to fall in along smooth, ordered streams, rather than through violent, irregular mergers. And it needs time for orbits to settle and stabilize. At less than 2 billion years old, that settling time should not have been available. One proposed explanation involves the temperature and flow of gas in the early universe. Some simulations suggest that in regions where dark matter halos were structured in a particular way, gas could flow inward along cool, narrow streams without triggering the disruptive heating that mergers produce. If those smooth flow conditions were more common in the early universe than models predict, disk galaxies could have assembled faster and survived more intact. Another proposal is that the first disk galaxies were stabilized by their own high gas density. Early galaxies contained proportionally much more gas than modern galaxies do, and some researchers argue that extremely gas-rich disks have a self-stabilizing property where the gas itself dampens the turbulence that would otherwise destroy the disk structure. Neither explanation is fully confirmed. Both require the early universe to behave differently from what the standard model calculates. But here is what makes this discovery particularly striking for anyone thinking about our own history. If disk galaxies were forming and surviving this early, then the conditions for a star like our Sun, forming inside a stable, organized disk, were available far earlier in cosmic history than previously thought. The window for planets, for chemistry, for whatever comes next in a habitable galaxy, opened much sooner than the models suggested. And some of those early disk-like galaxies contain something at their centers that has no clear explanation in any model, something Webb keeps finding and scientists cannot yet classify. They started showing up almost immediately, tiny, intensely bright, unmistakably red, scattered across Webb's deep field, images like small embers in a dark field. Scientists called them, with minimal ceremony, little red dots, and after examining dozens of them, nobody could confidently explain what they are. The redness comes from their redshift, the same stretching of light that Webb uses to identify distant galaxies. But the little red dots are red in a way that does not quite fit standard galaxy profiles. Their light distribution does not match the signature of a normal star-forming galaxy seen edge-on, which can appear red due to dust obscuring its light. It also does not match a standard quasar, the brilliantly lit core of a galaxy powered by an active black hole, though some of them have characteristics that overlap. What makes them genuinely strange is their compactness. Most are tiny in angular size, meaning they are either very small physically or so distant that their true extent cannot be resolved. But their brightness, given their apparent distance, implies an enormous energy output packed into a very small volume. More energy than you would expect from a region that compact. Based on anything in the standard model, several teams have proposed that the little red dots are a population of objects in which a very massive, actively feeding black hole is surrounded by a dense shell of dust. The black hole's accretion disk generates enormous energy. That energy heats the dust, which re-radiates it as infrared light, producing the red color. The dust would also hide the direct signature of the black hole behind it, making the object look compact and unusual, rather than showing the clear quasar features scientists know how to identify. If this interpretation is correct, the little red dots represent a previously unknown phase of black hole growth, an early stage in which the black hole is gorging on gas inside a thick cocoon of dust, before eventually clearing that dust away and revealing itself as a full quasar. But the numbers do not quite work out. There are too many of them. If every little red dot is a feeding black hole in a dust cocoon, the total population of black holes at that era in cosmic history would be far larger than the models predict. And the combined energy they are putting out would have measurable effects on the reionization of the universe that are not currently showing up clearly in other data. Some researchers have proposed a completely different explanation, that the little red dots are an entirely new class of object that the standard model does not include, something that forms through a mechanism scientists have not yet imagined. The data is not yet sufficient to confirm or rule this out. What makes them especially relevant to the larger story Webb is telling is that their existence adds to the population of early universe objects that exceed model predictions. Whether they are extreme black holes, exotic new objects, or something else entirely, their presence in such large numbers is another signal that the early universe was more energetic, more productive, and more strange than the models assumed. And while cosmologists work to understand the universe's largest mysteries, Webb has also been quietly doing something else, looking at small, rocky worlds nearby. And what it found there has a very different kind of significance. Webb was not designed only to look backward in time. It was also designed to look sideways, at the planets orbiting nearby stars, and specifically at the gases in their atmospheres. A planet's atmosphere acts like a fingerprint. Different molecules absorb different wavelengths of light. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. By analyzing which wavelengths are missing from that filtered light, scientists can identify which molecules are absorbing it. The technique is called transmission spectroscopy, and Webb performs it better than any previous instrument. In 2022, Webb analyzed the atmosphere of a planet orbiting a star about 700 light-years from Earth. The planet is called K2-18b, and it sits in the habitable zone of its host star, the range of distances where liquid water could exist on a planetary surface. Previous telescopes had detected signs of water vapor in its atmosphere. Webb confirmed that detection and added something else, a tentative signal for a molecule called dimethyl sulfide. Dimethyl sulfide is significant because on Earth, virtually all of it is produced by living organisms. Marine phytoplankton generate enormous quantities of it in Earth's oceans. It is considered a potential biosignature, a chemical sign of biological activity. The detection from K2-18b was tentative. The signal was weak and required more observations to confirm, but the fact that Webb's instruments could even detect such a molecule at that distance was itself remarkable. Webb has also confirmed carbon dioxide in the atmospheres of planets in other systems, including one of the TRAPPIST planets, a group of 7 rocky worlds orbiting a star about 40 light-years from Earth. Several of those planets sit in or near the habitable zone. Confirming carbon dioxide in their atmospheres gives scientists a clearer picture of their atmospheric composition and whether conditions could support liquid water. The detection of biosignatures remains out of reach for now. Webb was not designed specifically for that purpose, and the signals it can detect from exoplanet atmospheres are still too faint and too ambiguous to confirm life. But what Webb has done is demonstrate that the detection pipeline works, that the technique of reading planetary atmospheres from hundreds of light-years away is real, not theoretical. The next generation of telescopes, designed specifically for exoplanet atmospheric analysis with far larger mirrors and more specialized instruments, will be able to do what Webb is only beginning to sketch the outline of. They will read the full chemical contents of habitable zone atmospheres and look for combinations of gases that living organisms produce. Oxygen alongside methane, for instance, which react with each other and would quickly disappear without a constant biological source to replenish them. Webb is the proof of concept, and the concept works. But while Webb scans nearby skies for signs of life, its deep field observations are raising a question that goes in the opposite direction, about the age of the universe itself. And the answer Webb's data suggests is one that breaks a timeline scientists have been confident in for decades. Close is a relative word in science. For most of human history, the question of whether life existed elsewhere in the universe was purely philosophical. There was no instrument, no method, no measurement capable of addressing it with any rigor. It was a question for poets and priests, and scientists mostly set it aside. Webb changed that, slowly, but measurably. The path to detecting life from a distance requires several steps. First, find planets the right distance from their stars for liquid water to exist. Done. Astronomers have found thousands of candidate planets, and the number grows every year. Second, confirm that those planets have atmospheres. Webb is doing this now. Third, read the chemical composition of those atmospheres in enough detail to identify biosignatures. Webb is beginning to sketch the edges of this capability. Fourth, find combinations of gases that cannot be explained without biology. That fourth step is where the real challenge lives. No single gas proves life. Oxygen exists on some planets without biology. Methane can be produced by volcanic activity. Water vapor is everywhere. The signal scientists are looking for is not a single molecule, but a combination. A chemistry that only makes sense if something is alive and actively maintaining it. Earth's atmosphere, seen from space with a sensitive enough instrument, would look obviously biological. The combination of oxygen, methane, nitrous oxide, and water vapor together, in the concentrations Earth maintains them, is chemically unstable. These gases react with each other and break down on their own. For all of them to be present simultaneously in steady concentrations, something has to be constantly replenishing them. On Earth, that something is life. Billions of years of photosynthesis, respiration, and biological chemistry continuously pumping gases into the atmosphere. An alien civilization with a Webb-equivalent telescope pointed at Earth could likely tell that something biological is happening here. Webb cannot yet read a planet's atmosphere in that level of detail. The planets it can analyze are mostly larger than Earth, with thick atmospheres that produce stronger, more detectable signals. Rocky, Earth-sized planets in habitable zones are much harder targets. Their atmospheres are thinner and produce weaker signals that get lost in the noise at current distances. But a team of astronomers calculated that with enough observation time, Webb could potentially detect certain biosignatures on the TRAPPIST planets if they have substantial atmospheres. The calculation shows it is possible in principle, though it would require hundreds of hours of observation time focused on a single planet. That calculation mattered because it shifted the conversation from maybe someday to we have a telescope that could do a version of this now. The search for life outside Earth moved from pure speculation into the realm of instrument design and observation scheduling. Webb pushed that door open. What comes through it depends on what the next generation of telescopes finds when they walk through. And while that search continues, Webb's deep field data has been feeding a debate that cuts at one of the most basic facts about the universe: how old it actually is. A debate with an answer that challenges everything downstream of it. The universe is 13.8 billion years old. That number is not a guess. It is calculated from multiple independent measurements of the cosmic microwave background, the expansion rate, the abundance of light elements, and the age of the oldest stars. Every measurement, when run through the standard model, converges on the same answer: 13.8 billion years. Scientists have been confident in this figure for over 2 decades. Webb is making some of them less confident. The issue starts with the impossible galaxies, those massive, structured, chemically enriched early galaxies that exist only a few 100 million years after the Big Bang. As discussed earlier, their existence requires star formation processes, chemical enrichment cycles, and structural development that happened at rates the models cannot fully explain within the available time. One resolution to this puzzle, proposed by a small but growing number of cosmologists, is that the available time is actually more than the current model assigns. If the universe is older than 13.8 billion years, even by a few billion years, many of the impossible galaxies become less impossible. There would simply be more time for the processes that built them to unfold. An astrophysicist named Rajendra Gupta published a paper in 2023 arguing that a revised cosmological model, one that incorporates additional physics involving the changing strength of fundamental forces over time, could push the universe's age to as high as 26.7 billion years. That is nearly double the standard figure. The response from the broader scientific community was skeptical. Changing the age of the universe is a radical move. It would require discarding or heavily revising models that fit an enormous range of observations extremely well. The standard age is not derived from one measurement, but from dozens, all pointing at the same answer. Shifting that answer requires a mechanism that touches all of those measurements simultaneously and explains why they have all been consistently giving the same wrong result. That is a very high bar, but the conversation is happening. Webb's data has made it respectable to ask the question, even among researchers who find the alternative models unconvincing. The galaxies are real. Their properties are measured. If the current timeline cannot comfortably accommodate them, the timeline is the thing that needs to be examined. A more mainstream version of this question involves smaller adjustments. Some researchers believe the early universe had conditions, perhaps related to the changing dark energy discussed earlier, that allowed structure formation to proceed faster without requiring a different age for the universe. In this view, the age stays the same, but the model of what happened inside that age needs revision. Whether the solution involves a different age, different early conditions, or a completely new physical process, the debate Webb has triggered is genuine, and it connects to something that even more radically challenges the standard picture. The possibility that the universe we observe is only one piece of a much larger reality. The multiverse is a hypothesis that most scientists treat with careful respect and quiet discomfort. The idea, broadly, is that our universe is one of many, that the Big Bang was not a unique event but one of countless similar events, each producing a separate universe with its own laws of physics, its own initial conditions, its own history, We cannot see these other universes. We cannot communicate with them. By definition, they may be completely beyond any possible observation. So why do serious scientists take the idea seriously? Because certain physical theories, developed for reasons completely unrelated to cosmology, naturally predict that a multiverse should exist. String theory, which attempts to unify quantum mechanics and general relativity, requires extra dimensions and allows for an enormous number of possible universes with different physical constants. Eternal inflation, a model that explains why the universe looks so uniform on large scales, predicts that the inflationary period that launched our universe never fully stopped and is still spawning new universes in other regions of spacetime. These theories were not invented to explain the multiverse. The multiverse is a consequence of taking them seriously. Webb's data enters this conversation in a subtle but meaningful way. The precise measurements Webb is providing of the universe's large-scale structure, its expansion history, its early galaxy distribution, and its dark energy behavior can be compared against predictions made by different inflation models. Some inflation models predict a universe that looks exactly like what Webb observes. Others predict something measurably different. As Webb narrows down which inflation models fit the data and which do not, it is indirectly testing the class of theories that predict a multiverse. If the specific version of inflation that fits Webb's observations is one that also predicts eternal inflation and bubble universes, then the multiverse hypothesis gains indirect circumstantial support. This is far from proof. Indirect support for a theory is not confirmation. The multiverse remains untestable in the direct sense, because there is no observation that could definitively show us another universe. But science has a long history of accepting the existence of things that cannot be directly observed when the indirect evidence becomes overwhelming. Dark matter cannot be seen directly. Dark energy cannot be detected in a lab. Yet the evidence for both is strong enough that denying them requires inventing even more complicated explanations. If the multiverse continues to be the most natural consequence of the physics that best fits Webb's observations, it may one day reach the same status. For now, it remains one of the most extraordinary possibilities that Webb's data is quietly pointing toward. And as Webb maps the edges of what we can observe, it is also gathering light from a time so early that it may carry information about what came before the Big Bang itself. The Big Bang is the beginning of everything our current models describe. Time, space, energy, matter, all of it emerged from that initial state. Everything before that moment is, by the standard definition, outside the reach of physics as we know it. But some physicists believe the Big Bang was not actually a beginning, that it was a transition, a bounce, a moment where a previous universe or a previous phase of existence collapsed or transformed and gave birth to what we now call our universe. This idea has a name, the Big Bounce. In some versions of it, our universe goes through cycles of expansion and contraction. In others, the Big Bang was a collision between two higher dimensional structures called branes in string theory. In others still, the quantum state of a previous universe tunneled into a new configuration, producing our universe as a kind of bubble in a pre-existing medium. All of these models make a similar prediction. If something existed before the Big Bang, it may have left faint imprints in the earliest light we can observe. Specifically, in the cosmic microwave background radiation, the oldest light in the universe, which carries a detailed record of conditions just after the Big Bang. Certain patterns in the cosmic microwave background could, in principle, preserve information about pre-Big Bang conditions. Circular rings of slightly different temperature, for instance, have been proposed as a signature of collisions between universes in a cyclical cosmology model. Scientists have searched for these rings. Some claim to have found patterns consistent with them. Others argue the patterns are within the range of random variation. Webb is not a cosmic microwave background telescope. It studies visible and infrared light from stars and galaxies. But Webb contributes to this question indirectly. The large-scale structure of galaxy distributions, the precise measurements of inflation, the behavior of the early universe's density fluctuations, all of these constrain what pre-Big Bang conditions could have looked like if they existed. The more precisely Webb maps the early universe, the more it narrows the space of possible pre-Big Bang models. Some models predict specific signatures in early galaxy clustering that Webb would detect. Others predict the universe should look subtly different in ways Webb can measure. As Webb's catalogue of early galaxies grows, it is becoming a test of these ideas by elimination. Each observation rules out certain possibilities. The ones that survive the narrowing are the ones most likely to describe reality. Whether that reality includes a predecessor to our universe remains unknown, but Webb is making the question more scientific and less speculative with every year of data it collects. And all of this data, the galaxies, the black holes, the voids, the chemical signatures, is arriving at a moment when the institutions of cosmology are in a genuine state of upheaval. Science has a process for normal discoveries. Find something new, publish a paper, other researchers check the results, the community debates, the textbooks eventually update. It is slow, careful, and designed to prevent mistakes from becoming permanent. Webb is moving faster than the process was built to handle. In its first 2 years of full operation, Webb produced data challenging the standard model in more distinct areas simultaneously than any single telescope in history. Impossible galaxies, oversized black holes, chemical signatures that break the timeline, unexpected reionization rates, deviations in dark energy, a Hubble tension that refused to close, massive voids, early disk galaxies, little red dots with no clear classification. Each of these findings, individually, would generate years of scientific discussion. Together, they are arriving at the community faster than normal processes can absorb. Researchers are responding in real time. Papers are being published, challenged, and revised at an accelerated pace. Some established models are being quietly updated to accommodate Webb's findings. Others are being actively defended by scientists who believe Webb's analysis methods may have systematic errors that are inflating the apparent violations. The systematic error argument is serious and worth understanding. Every telescope has limitations. Every analysis method carries assumptions. If Webb's infrared photometry, the way it measures brightness in infrared light, has a calibration offset that makes distant galaxies appear slightly brighter than they are, that could make them appear more massive than they truly are. Some researchers have argued that a small calibration issue of this kind could explain a fraction of the impossible galaxies problem. Webb's team has responded to this by cross-checking measurements against other telescopes, running independent calibration tests, and publishing detailed uncertainty analyses. The calibration arguments have reduced the severity of the problem in some cases, but have not made it disappear. The core discrepancies remain. What makes this moment in science genuinely unusual is the openness of the crisis. Scientists are not hiding the disagreements. They are publishing them, debating them publicly at conferences, and in some cases, openly stating that they do not know what is wrong with the current model, but something clearly is. That kind of public uncertainty is rare in a mature scientific field. The standard model of cosmology is not collapsing, but it is bending under weight it was not designed to carry. And the amount of weight keeps increasing with every new Webb observation cycle. New discoveries are not coming in once a year. They are coming in continuously. The telescope never stops collecting light. The data pipeline never stops producing findings. And much of what Webb has already collected is still waiting to be analyzed. Webb generates data faster than it can be fully analyzed. Every time Webb points its mirror at a patch of sky, it collects photons across multiple wavelengths simultaneously. That raw data flows down to Earth and enters a processing pipeline. Computers apply calibration corrections, remove instrument noise, subtract background signals, and produce processed images and spectra that scientists can examine. That pipeline runs continuously, and it produces more processed data than the available workforce of astronomers can examine in real time. At any given moment, there are years' worth of processed Webb data sitting in publicly accessible archives that no scientist has yet studied carefully. Images of galaxy fields, spectra of distant objects, atmospheric readings from exoplanets, light curves from variable stars. All of it collected, processed, and filed away. Waiting, the scientific community is enormous but not unlimited. Analyzing Webb data requires expertise in specific areas, access to computing resources for modeling, and time that competes with everything else researchers are already working on. The result is a backlog, a growing library of observations that contain discoveries nobody has found yet because nobody has looked yet. This is not a failure. It is a consequence of unprecedented success. Webb is performing so far above its original design specifications that the volume of scientifically valuable data it produces has outpaced the human capacity to extract meaning from it. Some research groups are turning to machine learning to help. Automated systems trained to identify unusual objects in Webb images have already flagged several candidates that human researchers then followed up on. The little red dots were partially identified through automated searches of this kind. The algorithm found patterns that matched a signature of interest. Humans then looked at the flagged objects, and the scientific process took over from there. But machine learning tools are only as good as the patterns they are trained to find. Objects that do not fit any known pattern, truly novel categories of thing, require human recognition to identify in the first place. And the most important discoveries Webb might still contain could be exactly the kind of thing no algorithm is currently looking for. The treasure is in the archive. Every month, researchers dig into data that has been sitting untouched and find something unexpected. Some of those findings go on to reshape understanding in their specific corner of cosmology. Others open entirely new questions that require further observation. Webb is scheduled to operate for at least 20 years, possibly longer if fuel and hardware hold up. That means 20 years of data collection, with the archive growing continuously and the backlog of unanalyzed observations growing with it. Whatever is still waiting in the pipeline, whatever discoveries have already been collected but not yet seen by human eyes, represents a portion of Webb's scientific output that has not yet entered the conversation. And some of it may be the most important data Webb has ever produced. But Webb, for all its power, is already being designed around. The generation of telescopes coming after it are being built to go further, see sharper, and answer the one question that sits at the center of everything Webb has raised. Webb is the most powerful space telescope ever built, and it is already not enough. The discoveries it has made, the impossible galaxies, the ancient black holes, the Hubble tension, the hints of a changing dark energy, have produced a list of follow-up questions longer than the list of questions it was launched to answer. Science works that way. Every answer opens 10 more doors. Webb has opened more doors than any single instrument in the history of astronomy. The telescopes being designed now are built specifically to walk through those doors. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will survey the sky in infrared across an area 100 times wider than Webb's field of view in a single observation. Where Webb stares at tiny patches of sky in extraordinary detail, Roman will map enormous swaths at once, producing a census of galaxies, dark energy signatures, and gravitational lensing events on a scale that would take Webb decades to accumulate. Roman is specifically designed to attack the dark energy problem and the Hubble tension with statistical power that no previous instrument could provide. On the ground, the extremely large telescope being built in Chile will have a mirror nearly 130 feet across, roughly 6 times the diameter of Webb's mirror and far larger than anything currently operational. Its resolution from the ground aided by adaptive optic systems that correct for atmospheric blurring in real time, will rival and in some ways exceed what space telescopes can achieve. It will be capable of directly imaging the atmospheres of Earth-sized planets around nearby stars. The biosignature search that Webb opened the door to, Roman and the extremely large telescope will walk through, a proposed future mission called the Habitable Worlds Observatory, is being discussed by NASA as a dedicated exoplanet atmosphere analyzer. Its explicit goal is to find biosignatures on rocky planets in habitable zones. It does not yet have a confirmed launch date, but the scientific consensus behind it is growing. Webb gave the community enough confidence in the technique to justify the investment. Each of these instruments builds on what Webb taught, about where to look, about what signals to search for, about where the models are failing and what new observations could fix them. The one question that drives all of it is the same question that has driven astronomy since the first human looked up at a dark sky. Are we alone? Webb did not answer that question, but it changed the terms of the debate. It showed that habitable zone planets have atmospheres that can be read. It showed that the chemistry of those atmospheres is accessible to the right instrument. It showed that the search is real, practical, and pointing toward a specific generation of telescopes that will be capable of a specific kind of answer. And it showed, through everything else it found, that the universe is far stranger, far more energetic, and far harder to explain than anyone who built the standard model expected. The universe at its edge is not quiet. It is not empty. It is not simple. Webb looked, and what it found is going to take the rest of this century to understand.